Turning now to the work of 17th century German astronomer Johannes Kepler. He published two influential works, New Astronomy in 1609 and Harmonies of the World in 1619. Kepler's three laws were, respectively, one, about the shape of the orbit of planets around the sun, two, about the motion of a planet as it goes around the sun, and three, the relationship between the different planets and their different respective orbits. So Kepler caught the attention of the astronomy world by working on the Copernican model and coming up with this theory that the relative spaces of the different planets in orbit around the sun could be accounted for by regular geometric shapes. So it had this beautiful Platonic kind of ideal to it. This idea turned out to not pan out, but it caught the idea of many people, including a guy by the name of Tycho Brahe. So the first law, what is the shape of a planet's orbit? So it is in the shape of an ellipse. So planets orbit in ellipses with the sun at one focus, and the other focus is just an empty spot in space. But he only discovered this after proving himself wrong. So the early work on the solar system was the Ptolemaic solar system, which was the geocentric system, that the Earth's within the center, because obviously the Earth doesn't move. We can tell that the Earth doesn't move, everything else must go around it. But this posed a problem in that when we looked up into the sky, we saw certain stars that tracked across the sky differently than the rest of the stars. These got named planets, planet meaning wanderer in Greek. And these planets would wander across the sky differently than the other stars, and sometimes they would go backwards. This is called retrograde motion. So if you have a simple system where you have kind of everything rotating around the Earth, the whole sky rotating around the Earth, why would some of these little star-like things that they called planets, why would they ever go backwards? So the solution to this was epicycles. So instead of just being in orbit around the sun, you would have little orbits around the orbital path, and this would account for retrograde motion. Of course, in the 16th century, a guy by the name of Nicholas Copernicus, who was in Prussia, which we now call Germany, the Copernican system had the idea of putting the sun at the center, and the planets just follow circles, and you can explain the retrograde motion in terms of the relative motion of the Earth. That if you look at Mars, for example, and it appears to move backwards in the sky from where it had been going, you can account for it by just saying, well, it kind of got passed by the Earth, and so it looked like it went backwards, but actually it didn't. So it's all relative motion. In the Copernican system of the heliocentric solar system, the sun being at the center of the solar system, Galileo is famously put on trial for teaching it, gotten afoul of the Catholic Church. So in the 16th century, along came a Danish astronomer by the name of Tycho Brahe. He had high-precision observations from his time in the sky. He was considered to be the last great pre-telescopic astronomer, making observations with the bare eye instead of with the telescope. And Johannes Kepler had caught his eye through some of his earlier work. And so Brahe had hired Kepler to be his assistant, and Brahe kind of had a problem in that he couldn't quite work out the orbit of Mars according to the solar system that he came up with. He had his own taconic system. And so he handed it to Kepler, his assistant, and said, you go work out the orbit of Mars. Now, Kepler did believe in the Copernican model, not the taconic system that Tycho Brahe dreamed up. But he had Brahe's data, and he studied Mars. And fortuitously, it would be that he studied Mars, because Mars had an orbit that was the most uncircular of all the orbits that he could have been asked to study. He made this discovery that in looking at the data that Tycho Brahe had on the location of Mars, that he couldn't make a standard circle fit for the motion of Mars. No matter how he tried to move it, even if he tried to go do like an off-center circle, it couldn't fit. So finally he stumbled upon the idea that it had to be following an elliptical orbit. And as we now know, this is how planets orbit. They orbit in elliptical orbits. And again, it was fortuitous that Kepler was looking at Mars, because Mars is actually the most eccentric of all the orbits, meaning the orbit that is the furthest from a circle. So it was fortunate that he was studying that. So that's the first of Kepler's laws, that planets move in ellipse. The second of Kepler's laws was, well, how does a planet move within this orbit? And this is the equal areas and equal times law. A line joining the planet and the sun sweeps out equal areas and equal time. But the amusing thing is that Kepler got to this law, which is true, which is exactly a true law, but he got to it by accident, involving a series of assumptions that were either only approximately true or flat out wrong. So he assumed a couple of things, and my source on this is a book called Physics, the Human Adventure by Gerald Holton and Stephen Brush. Basically, he said, okay, planets are driven around the sun by a force from the sun. They have to get pushed forward. So again, this is pre-Galileo, pre-Newton. We were believing in Aristotelian physics that you had to push something for it to be moving. So that was just completely wrong. And then he also believed that the force should be proportional to 1 over r, basically on the reasoning that the force should spread out equally in the plane of the planets. So you're spreading out the force over basically the circumference of a circle, so that's a 1 over r dependence, because Kepler reasoned that gravity wouldn't spread equally in 3 dimensions. That would be a waste of gravity. Next, he said that the velocity that the planet can move around the sun is proportional to the amount of force that's pushing it, and so therefore the velocity should be proportional to 1 over r. And of course, we know this is completely wrong. The velocity is not proportional to the force. That's the Aristotelian idea of physics. Assumption number 4, since the velocity is proportional to 1 over the amount of time to cover a short piece of the orbit, that this would mean that the radius should be proportional to the amount of time to cover any one piece of the orbit. This is approximately true if you're dealing with elliptical orbits. He also assumed that the area swept out, therefore, would be proportional to the overall time, which is, again, approximately true. And he kind of reasoned with this picture here that the radius is kind of sweeping out a bunch of area, and so the amount of time it would take would be proportional to the area being swept out there. And then his last assumption is that the orbit is a circle, which sounds kind of strange because it seems to contradict his first law that the orbits follow ellipse, but he actually discovered his second law before his first law, and so of course we know orbit is a circle is only approximately true. It's not really true. But he put all these things together and he came up with his equal areas and equal times law, which actually turned out to be true. Why is it true? Well, consider a planet in orbit around the sun and consider the torque due to gravity at any place in the orbit. So you can see the planet at different places in the orbit. You can see this is a very exaggerated elliptical orbit just for effect. And if you draw the lever arm from the sun to the planet in each of these different locations, and then you draw the force of gravity. Of course, the force of gravity is always just straight towards the sun from the planet. So you can see the lever arm and the force are always anti-parallel, meaning that the angle between the lever arm and the force is 180 degrees. So the force of gravity never causes any torque. And this is true of any radial force. That because the force is always radial, you're never going to cause any torque. This means that angular momentum is conserved. So we can use angular momentum conservation to come up with a legitimate proof of Kepler's second law. So remember I told you that the cross product of two vectors can graphically be thought of as the area of a parallelogram that's kind of trapped between those two vectors if each of those two vectors is a side. Well, you can reason that the area covered can be the cross product of r, which is kind of your lever arm there from the sun to that point in the orbit, crossed with dx, where dx is a little piece of the orbit that's been covered. And I can replace dx with just v dt. So just how fast I'm going at that point in orbit times dt, a short little period of time. That's just speed times time gives me distance. So that would mean that the rate of the area covered with respect to time, if I divide both sides by t, is just going to be half r across v. And r across v is basically just m away from being angular momentum. So what you're getting is that the area covered per time is proportional to the angular momentum. And so really this equal areas, equal time statement is equivalent to conservation of angular momentum, which again happens for any radial force, any centripetal force. So those are the first two laws, but what Kepler really wanted was another law, something that would relate the motion of the orbit of one planet to the motion of all the others, and to unify them together in a beautiful grand harmony, so much to the point that he called this, the title of this book he published, Harmonies of the World, and he called this his law of harmonics. Basically, he had these observations about the period of time that it took various planets to go around the sun once, and the distance that each of those planets was from the sun, but really the semi-major axis, meaning the distance from the center of the ellipse to the long end of the ellipse. And it turned out, I don't know exactly how he came up with this law, but there's a quote in Physics: The Human Adventure that Kepler, after unceasing toil through a long period of time using Brahe's observations, discovered the true distances of the orbit. At last, the true relation overcome by storm the shadows of my mind with such fullness of agreement between my 17 years' labor on the observations of Brahe and this present study of mine that I at first believed that I was dreaming. So 17 years of looking through observations, finally Kepler came upon his third law. And you can use the amazing technology of log-log paper to see that you will get a straight line on log-log paper, which is equivalent to the fact that the ratio of each of these variables raised to a power is always constant. And so Kepler's third law is just that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. Again, the semi-major axis here is just a line that goes from the center of the whole ellipse to the furthest edge away from it. So how do you prove Kepler's third law? Well, there is kind of a little proof that they actually do require you to be able to know how to do on the AP exam, just because it's so simple. And it mirrors something that we did earlier when we looked at how potential energy and kinetic energy in circular orbit compared. So you set F equal to ma, and then you say that the force is equal to the gravitational force, gmm over r squared, and then you say since you're in a circle, you can set the acceleration to v squared over r. You can cancel out an r, you can cancel out little m, and you get to gm over r equals v squared. Plug in that v is equal to the distance over the time, so that's 2 pi r over the time to go around the orbit once. You rearrange a couple things, and you get to t squared over r cubed is equal to 4 pi squared over gm. So you get to Kepler's observation that the period squared divided by the radius cubed is going to be a constant, and that constant depends only on the mass of the thing that you are orbiting. So if you are orbiting a larger mass object, like the sun, for example, this means that you have to orbit faster, or that you have to be further away from it. So let's do a quick example of this. So Mars has an orbital period of 687 days, so it's about 2 Earth years. How far is it from the sun? So you feed it straight into this ratio. So you get the period of the Earth, which is, of course, 1 year, 365 days, over its distance, 1 AU. We've defined 1 AU to be the distance between the Earth and the sun, is equal to 687 days, the period of Mars, divided by the distance that Mars is from the sun. So you work it out, and you get that the distance that Mars is from sun is 1.5 AU. So Mars is on average 1.5 times the distance away from the sun as Earth is. You can also use the same trick to figure out the altitude of a geosynchronous orbit. We talked about a geosynchronous orbit as being a satellite that has an orbit with the same period as the Earth, so that it always stays above the same point in the sky in Earth. So that would mean we plug in for the period 24 hours, but you should change that into seconds. So you get 24 hours times 3600 squared. And then you can just plug in m, the mass of the Earth, the mass of the thing you're orbiting, solve for r, and you will get that r, the radius of orbit, has to come out to be about 42,000 kilometers, which is not the right answer. The right answer is, for the altitude of a geosynchronous orbit, about 36,000 kilometers, as shown earlier. And of course, the difference is the radius of the Earth. So when we're dealing with orbital dynamics and orbits, we haven't considered the fact that the object that we're circling has a radius to it. So the altitude, recall, is the distance between the orbit and the center of the planet minus the actual radius of the planet. So you do have to do that. Now, you might object in that I kind of used in this derivation here equations that were set up for circles, and didn't we just say that these are really elliptical orbits? Well, it makes the math a lot easier, but basically this derivation will hold up because as long as you're in a pretty reasonably close to a circle ellipse, then you can still say that the acceleration is v squared over r to a very close approximation, and v is still going to be the distance over time, and the distance really is still going to be proportional, and the distance around the circle still really is going to be proportional to the average distance that you are from the object that's causing gravity. So this derivation holds up well enough when you translate it to ellipses instead of just circles.